Hello everyone, today I wanted to talk about AI and try a few things, none of which really worked perfectly. But first of all, do you remember the good old days? Back when AI was a matter of computer science, an extension of mathematics, and people only heard about it in science fiction or when Rob Miles was talking about it on Computerphile. I highly recommend those videos. Or when researchers trained it to play a video game and it found a bug or an exploit in how its goals were set, and people said it outsmarted its creators and the future was now. Those were the good times, but then something horrible happened. The NFT bubble burst, and all the grift bros on the internet were looking for a new buzzword to work with, and around the same time, generational adversarial networks, a generally somewhat clever idea, became publicly available, and with enough data of dubious source became decent enough to produce images that were not straight up eye cancer. So of course they took to it and flooded the internet in slop, much of which I cannot show you on YouTube, and a whole debate started over whether this was true art or ethical. It's not. Now, that much is arguably obvious, but also for some reason entrenched in a lot of drama, which isn't really what I want to go into here, because what I noticed is that a lot of this debate is focused on image generation versus drawing, but really there's a lot more humans can do that people are trying to replace with AI, and so just as an experiment, I said, I want to try replacing myself with AI, just to see how well it could theoretically do. So there's two things I do that I wanted it to try, but couldn't really copy over one-to-one, but tried to look into how well it could theoretically do. The first is that I make 3D models that you can buy online for 3D printing, most of it cosplay stuff, some other stuff like rocket miniatures, and theoretically, there's some thought going into this about how to interpret drawn shapes, how to turn them into solid CAD models, how to keep them practical, how to scale them right and make them look right, how to make them sturdy and printable. But generally, that's mostly finding points on an image, measuring them out, doing some math. Computers have been able to find and recognize and correlate points on images before. This should theoretically be sort of doable, right? Now, I'm not actually looking to outsource my work to AI, and most of the image-to-STL AI generators require a premium membership or payment per attempt. So instead, I looked at a gallery of already made AI-generated models that you could play around with or recombine, and that were apparently deemed good enough to be used as a showcase or as a gallery of things you can play around with. And I selected a few that I think are kind of representative, that we can actually check for quality because they represent something that actually exists rather than a generic asset, and that we can check for overall quality. The first one is this bust Gundam Unicorn. So for comparison, I've got this Google Images search for Gundam Unicorn open, and I'm not going to go into every tiny detail. There's small inaccuracies everywhere, but well, there's a lot of Z-fighting going on. That's the first thing you notice. The chest and the sides of the head look decently accurate. I mean, you can't get it perfect when there's different reference images. The top of the head is a bit too shallow and doesn't go far enough back. The face is, well, it's hard to tell because of the Z-fighting, but it seems flat and seems to lack any details that might be there depending on which reference exactly you go off. The horn isn't really accurate either way. This detail here should go through as one part. If you go off this, or if you go off other references, then it shouldn't be there at all. And either way, this should be one triangle and shouldn't change cross-section like this. The forehead is a bit of a mess, and big surprise, let's turn it around. Well, the back of the head is kind of open, and there's this inside, whatever this is. Now, these models aren't specifically made for 3D printing. They're made for, like, using them as references for meshing them together and using them as references for more AI-generated models. But, like, if you're gonna make a 3D fan animation, you're gonna need the whole robot. So presumably this, as it's a bust, it is probably meant to be manufactured at some point, put on a desk, be it 3D printing, CNC machining, whatever. Yeah, that's gonna be a bit of a problem. And what's up with the Z-fighting? How many models are there stuck inside each other here? What is going on in the forehead? What am I looking at here? Exactly. But, I mean, some parts of it are okay. It's not as terrible as I could have imagined. It's also not as good as I could have imagined. It could be better, could be worse. Now, model number 2 is simply named plain Boeing. So it's not a specific aircraft type. They've got a manufacturer, but no aircraft type. It's not a Boeing 737 or 747 or 757. It just says Boeing. So we can't directly compare it to a specific type. I don't think there is a type that looks exactly like this. The wingtips are way too wide, too deep for anything I could think of, and the tires seem a bit wide. It's also a bit low poly. But it's overall decent. I'm not sure how exactly the windows are worked into the model. It seems a bit odd. And the doors, it's hard to tell exactly, but you've got this low poly line. If you use that as a reference, it seems like the doors are slightly different height. It's not perfect, but if you want a generic airliner model as an asset for a simple animation, if you just need a low poly generic airliner, it's okay. Now, model number 3, another vehicle based on an actual vehicle this time, so we can actually compare it. This says it's a Koenigsegg Agera, and I've looked up some images of that. There are slightly different versions. This model has the rear spoiler kind of growing out of its rear side like that. The only version I could find that looks remotely like that is in this article. It's still a lot less pronounced here. And also there's some other weird details. There's that kind of third middle wedge hump along the rear that's not real. There's this line that disappears when it reaches the door. This detail is only there once in the original, and it's doubled, and it kind of cuts way too far forward here. It's a bit inaccurate, and you can tell it's kind of smushy, it's kind of melty, it's not really a high quality model, but well, cars aren't my specialty either, so I can't judge it too hard, I guess. It's mediocre. Now the 4th model, this is not perfect, but it's by far the best one I've found in this gallery. There's no Z-fighting on the model. There's some Z-fighting going on in the background. I'm not sure what is there or why there's anything there, but okay. Not my problem. This is said to be a Thompson submachine gun. From the side view, it looks pretty okay. Now if you look at it from the top, it looks a bit narrower than the original. Bit hard to judge, but it's decent. Now if you look at it from the front, and you look at it from the front very precisely, the muzzle, barrel, they're not cylindrical, they're not circular, They're elliptical. They're a bit narrow and tall. And I'm not a huge gun nerd, but I don't think that's how bullets work. I think they're round and they like spin as they come out. It's not going to work like this. Other than that, it looks fairly decent. I would suspect that it's probably taken from like several decently chosen, high-quality reference images. The shape isn't too complicated, so it could recognize a few points, cross-reference them, measure them out, and map them into a 3D space. So it's closer to photogrammetric 3D scanning than AI generation, really. And during that, it might have slightly misjudged the perspective and thus slightly squished it. I guess you could theoretically get this model and stretch it in width a little bit and get a detailed model, a decent model. I'm not sure how detailed exactly it is. It has text on it. Is that text? Is that actually engraved or is it texture? I think it's texture. But yeah, by far the highest quality one I could find, even though it's a bit flawed, it's a bit squished, and there's something in the background that shouldn't be there. But I guess you could delete that if you download it. But now we get to the fifth and final model, the punchline, the segue. I have to prepare you for this. I'm not going to be too cruel to it. I'm not going to explain every single detail that's wrong, because then we'd be sitting here for days. There's not much that is right about it, and it's something that I'm a bit more nerdy about. It's a complex moving structure. It's difficult to turn into a simplified 3D model. I'm not going to be too mean to it, but that's a relative term. I present to you the International Space Station. And why does it have the Berliner Fernsehturm stuck in the middle of it? And all the Z fighting is back, and there's a radiator missing, and this robotic arm is coming out of the wrong module, and what's this? Is this supposed to be a spacecraft with landing legs or an antenna? Is this solar panel even attached? What's this plate in the middle? Did they merge the Zwister module with the ATV, and in the process it got fatter? I mean, you can, at first glance, recognize what it's supposed to be. But that doesn't mean that anything about it looks remotely right. What in the actual fuckery is going on here? So with that, ranked from best to worst, the Samson submachine gun, it's the only one where I'd say, okay, this is actually a decent quality model. You'd have to do a little bit to fix it. That's not perfect. It's slightly flawed, but it's okay. Then the generic plane, it's not supposed to be based on a specific aircraft type as a simple generic plane that's just meant to be a background asset in some video. I guess it gets the job done. Followed by the Koenigsegg Agera. Few details wrong, slightly melty, smushy model, mediocre quality, not great, not terrible. And we get to the Gundam. A few things wrong. Back of the head is, well, it's a mess. The model is a mess. There's a few things right about it, I'll give it that. A few things. It's bad, but I can tell that there are some details that are not bad. it's overall bad, but I can see a few things that are right, and then we get to the abomination. However this came to be. Probably a vague impression of what images of the ISS look like, smushed together in some neural network, then creating a 3D model basically from memory, which is basically a wide truss structure with these notable 8 solar panels and then stuff stuck to it. I guess if your recognition of the ISS comes down to that basic shape, then well, you could draw that in 5 seconds in Paint, but okay. Overall verdict, no, it's not working great, but I can see that there are individual cases where it sort of kind of works. To be fair, that is a model that you could basically look at one side view image of and kind of cut out and then do a few corrections and add a few details and get a decent model of it. So as far as turning an image into a 3D model goes, this is one of the easiest exercises we've seen in this collection. And also note that it is, specifically when you look at it from any other perspective than that side view, that you start noticing that something's a little bit off. But as a best case example, I think it works. Now the second thing I do is doing some automotive aerodynamic design and some early concept studies for a startup, and a lot of it is under NDA, so it's not like I can just take stuff that I'm doing for someone else rather than myself and that is under NDA and try to get AI to do the same thing and film it and just put it on YouTube. But what I can do is think up a few slightly trickier quiz questions about aerodynamics and rocket science and engineering that I can ask to text AIs. I picked to ChatGPT because it was commonly recommended when I just googled what AI should I use for technical questions, what AI should I use for physics questions. The common recommendation was either don't use any, just read your damn physics book and do your damn physics homework, or use ChatGPT. And the second one is, well, Grok, because, it's the AI, in air quotes, made by Musk, the rocket science genius. So clearly, if I ask it, if I quiz it about rocket science, clearly it's gonna be right about everything. It's gonna be promising. It has to know, right? It's made by the guy who's gonna get us to Mars, right? Right? Well, there's enough discussions and enough people arguing about whether Starship is ever going to work, and that's not the topic of this video. So instead, I thought I'd make up a few quiz questions, explain them to you, explain the trick to you, and ask them to these AIs to see what happens. Now, the first question was, if I design a car add-on made of plastic that's going to move at 100 miles per hour, is there a rule of thumb I can use to make sure the finer details don't get broken off by the wind? There's a rough rule of thumb that I thought they might come up with, which is to keep the aspect ratio of any cross-section below half the square root of the ratio of material strength to dynamic pressure. That way, at least that force can't just break them off. Neither of the AIs came up with that. Both of them went into more details than I initially expected. Some of it is good advice, some of it is slightly wrong. Grok started out with minimize drag and stress concentrations. That's decent advice, depending on the purpose and the shape. That's not always possible, but sure, obviously. Material strength and flexibility. Yes, make it of a decently strong material. Avoid brittle plastics. Now, brittleness isn't really that big an issue with aerodynamic forces themselves, more with hits and bumps and vibration. Thickness, it just tells us to make it thick and scale it up. It doesn't really tell us how to calculate this. Calculate wind loading, it gives us a basic drag formula. This is like middle school physics. It's the first thing you find when you look it up. It's okay. Technically, it's kind of useless because unless you have a CD value, you can't calculate this. And you find the CD value, well, either you roughly estimate it from empirical data, you look it up for a similar shape, you find it in a lookup table for a wing profile or something. Be sure you use the same reference area. But in the end, you calculate CD by using this formula in reverse. So first you need to find out drag through a CFD simulation or a test or reasoned from other physics, from conservation of momentum and how air is diverted. It gives us the approximately correct density for air at sea level, it does a correct unit conversion, then does this, and if you actually run the math, no, that's closer to 6.2 newtons. It does recommend using a safety factor. It doesn't tell us how to calculate how that force translates into a yield strength with the ratio of applied areas, or with the force over applied area, or the ratio of pressure over the ratio of applied areas. It doesn't tell us how leverage amplifies it, or how different points in a cross-section contribute differently to the moment that's holding on against the torque. It does talk about vibration and fatigue. That's also decent advice to think about that, but it gives us a basic formula for the natural frequency of a basic spring pendulum. This gets a bit more complicated if you look at a distributed force, but it also tells us to do an FEA simulation, and if you plug that into that formula, then you get a decent result you can work with. It doesn't tell us how to properly estimate that by hand for a plastic detail. It also doesn't tell us how to estimate the frequency that aerodynamic forces are gonna excite it at. This estimate, it's over a whole order of magnitude, and it seems a bit low. I mean, the frequency, it depends a bit on shape, that gets a bit complicated, but it's basically based on the ratio of speed to the size of the detail that you're looking at, to the size of its rear cross-section. And for a car going at 100 miles per hour, shedding a vortex behind it, that seems a bit high, but for a tiny detail on a plastic part, it seems very low. And it kind of just tells us to run with this estimate. Damping, well, this is good advice, but kind of under the wrong headline. Having elastic materials inside attachment points means that stress concentration gets distributed a bit better, but that's not actually fighting the vibration itself. Testing and prototyping, that's more like obvious but not very helpful advice. Tapering thin features, I mean, if you want to save material, but in the end, that doesn't actually add to the strength. Just the base cross-section has to be strong enough. If you taper it, that's okay. If you don't taper it, that's not going to make it weaker. Integrate supports. It doesn't really explain why things like support ribs can increase the leverage over which a force is distributed, but it tells us to. And that's about it. Now, if we move on to ChatGPT, it gives us similar advice. Again, a rough guideline for thickness, but it doesn't really put that into relation to anything or tells us how to calculate any of this. It just tells us to use smooth shapes. Tapered shapes is still it's not really helpful, but sudden edges, that's not really how airflow works, but sudden edges can increase turbulence, which is a problem with vibration, and sudden edges can lead to stress concentrations, which is a problem with structural strength. So using smooth shapes is actually helpful. It tells us to do that, not quite for the right reasons. It does tell us to calculate wind pressure rather than the drag formula, which is a decent starting point for a rough estimate. I think it's a bit smarter in doing that. And gets the calculation right. This is a correct outcome for this calculation. It does tell us to keep in mind that vibration and flutter and fatigue exist. It doesn't tell us anything about natural frequencies or how to calculate them. Grok wasn't very in detail or accurate about that either, but here we just get nothing about that. Mounting matters. Mechanical fasteners greater than adhesives at this speed. It's decent advice, but not really just because of strength, but more because of practicality and long-term reliability. Plastic type is key. Yeah, they differ in strength. Thickness isn't a material property, but okay. Quick design tips. Keep small details below the boundary layer. It's a good idea if that's possible for the purpose you're going with. Doesn't tell us how to estimate how large that is, but it gives us an estimate that is decently accurate for an average car. Use fillets, avoid sharp corners. It gave us the wrong reason for that, but that is good advice. Simulate or test with a wind tunnel. Good advice, obvious, not really a helpful rule of thumb during design. Consider printing prototypes in TPU or semi-flexible filaments for impact zones. Not sure if that's good advice, because using a flexible material helps you with vibration resistance over time. If you're going to make a prototype for testing the strength of a part, you don't want to give the prototype an advantage that the final product isn't going to have. Not sure if that's a good idea. Now, I realized this was probably not the best kind of question to test it with. It's relatively open-ended, which allows them to kind of just ramble on and throw many ideas and details in there while not really going into detail on any of them, and just kind of throw out very obvious advice here. So next things, I went a bit more into rocket science and gave them a bit less open-ended, more closed quiz questions with a direct number to calculate or yes or no to find out. Now with question number 2, I got a little bit cleverer at quizzing and got into a little bit more fun rocket science, and this is actually a trick question. You can try it for yourself if you like. It is a double trick question, and it is a basic calculation, so there are different potential numbers they could come up with that we can check against. A hypersonic glider with a glide ratio of 3 is released at a speed of 6,000 meters per second. Estimate its maximum range. I've got 4 potential answers prepared for this, and I'll explain the trick to you. If you want to try it out yourself, you can pause for a moment, and I'll go on and explain the trick and reveal the different answers. So, the first answer you could come up with is complete failure, unknown. This is the answer you'll come up with if you have a calculator and Google and no idea what you're doing. If you Google how to calculate range from glide ratio, okay, height times glide ratio, we don't know the height, it's not in the question, so the answer is unknown. The thing is, at this speed, you're going to be carrying a lot more kinetic energy than potential energy, so if you want to get a rough estimate, what you want to do is calculate the specific kinetic energy, convert that into a height, and use the glide ratio on that. If you do that, you get 5,504 kilometers. There's a few different assumptions and estimates you can do. You might be using 10 or 9.81 for gravitational acceleration. There's a bit of range to all of these answers, but roughly around 5,500 kilometers. You still fell for the trick. You know middle school physics, but you don't know rocket science. You don't know orbital mechanics. You still fell for it. But at least you got a result. What you also have to take into account is that at this speed, you have a significant centripetal acceleration as you go around the Earth. You're basically subject to orbital mechanics. You're not quite at orbital speed, but the fact that you're approaching orbital speed significantly reduces your effective weight, and that increases your glide range. If you take this into account, you get 8,210.213551 kilometers. And then if you make a decent assumption about the altitude that you'll glide at the speed and how it changes and how much energy you get from that and how gravity changes over altitude, if you take all the details into account with the information in the question, the best, decent, most plausible estimate is 8,313 kilometers. Honestly, anything between 8,000 and 8,500 I would count as a correct answer. Now let's see what Grok does with this. It repeats the question to us in the typical AI corpo drivel that we're used to. Assumptions: the glider is released at high altitude, and we assume it glides until it reaches the ground. The initial speed is used to infer the glider's behavior, but we assume steady gliding. Okay? And you haven't been given any other number than that one glide ratio. We ignore drag losses. That would make the glide ratio infinite, but okay, whatever. Glide ratio and glide angle? This is useless. This converts the ratio to an angle, but you only need the ratio. You're not using this anywhere later. Gives us the basic height times glide ratio formula. The problem does not specify release altitude, I know! We just roughly estimate the altitude. Very roughly estimate the altitude, and just invent a number out of nowhere, use that. Say that speed plays a role, but don't actually take it into account. So okay, it might be at a higher or lower altitude. Let's refine those potential answers. Yeah, that's a fail. You can use Google and a calculator, but fail middle school physics. Let's look at ChatGPT. ChatGPT is a little bit smarter. It also repeats the question and tells us what glide ratio is, but it says approximate using energy. Convert kinetic energy into potential energy. Solve for height equivalent. Gets a height equivalent, applies the glide ratio to that, and gets 5,504,586 meters, or 5,504.586 kilometers, rounding error, different assumption for G, something like that. It's close. Final answer, maximum range 5,500 kilometers. Actually, no, it fell for it. It didn't fall for it as badly as Grok. But it still got the middle school physics but fell for the trick question answer, but hey, at least it's not completely useless. It knows middle school physics. Question 3, once again rocket science, once again a basic calculation with an answer and not a general ask for advice. Again a bit of a trick question if your knowledge of rocket science is limited, but this time it's a bit easier because it's a type of calculation that is mentioned in a lot of textbooks on rocket engines. It's not directly copied. I could have taken example questions from books like Rocket Propulsion Elements, but there's like PDFs of that available online. So if you just copy an example problem from there, either the AI, if it has dynamic access to the internet, it can Google that question basically and find that question in that PDF, or it's potentially trained on some of that text and just has that question and the correct answer in its training data. So I came up with a bit of a trick question of my own. It might not be as difficult because if you know what topic it's about and you just Google the basic equations involved in it, you kind of get to the right answer. If a rocket engine has a chamber pressure of 200 bar and a nozzle ratio of 80, is that above or below the ideal expansion for use at sea level? The very obvious but wrong answer, if you don't know much about rocket engines, would be that's below ideal expansion, because 80 is less than 200, so you expand by 80, you start with 200, so you come out with more than 1 bar of pressure, so you could expand it even further. But there's 3 reasons why that's wrong, and I mean really you have to look at the actual equations, but there's 3 simple explanatory reasons for why that's wrong. Number 1 is the density ratio and the pressure ratio isn't the same. If you expand a gas, its temperature decreases, so its pressure reduces by more than its density. The second part is that as the exhaust goes through the engine nozzle, it accelerates, so the volume flow rate increases more than the area. And the third reason is that when the exhaust gets into the throat of the engine, it's already at a lower density and pressure than it is in the chamber. And I've specifically selected those numbers so that with typical properties for rocket exhaust, if you take 2 of these factors into account, you get the right answer, but if you only take 1 of these factors into account, you don't. And of course, if you know the correct equation, you get the right answer. And in this case, it actually seems both AIs look up what looks like the right equation. I'm not sure if that's a good estimate for the heat capacity ratio, because at high temperatures, rocket exhausts are usually closer to 1.2, sometimes even slightly below. Without checking all of the math, the result is approximately correct, and yes, it is overexpanded. And ChatGPT actually gives us the same result and gives us some rough advice for typical expansion ratios here. So in this case, where the correct answer is based on a formula you could easily look up, they do get the correct answer, even though I would consider this slightly higher math than the question before, because it's a bit less of a trick question and it's more of a known formula. They got it right, even though it's arguably a slightly more complicated question. Of course, that could be a bit of a problem for people using AI in practice, because the fact that, I mean, this isn't really that complicated. It's like the first chapter in every book on rocket science, but to someone not familiar with the subject, it looks slightly more complicated, whereas the former one was middle school physics with a little trick question included. But because of that trick question, they got it wrong, while they got this one right. So you could look at this, see they got it right, assume AI knows stuff, and then later on fall for a much simpler but slightly trickier question. Next question, we're sticking to the same Roth topic, using the same equations, which they apparently know, but we're making it a little bit more of a trick question again, and we're asking something that isn't mentioned in the first chapter of every rocketry book, though it is something you can look up online. What's the theoretical maximum compression ratio for a scramjet traveling at Mach 4? You use the same equation. What you're basically doing here is you're taking the kinetic energy of the air and converting it to compress the air and see how far you can compress it. You can normalize that for the temperature of the air and the speed of sound cancel out, so with the Mach number you can calculate this. In this case, I helped out Grok a little bit, because Grok told us about the practical design of the air intake of a scramjet, but the question was about the theoretical maximum. So I asked it, okay, but with multiple shocks, what would be the theoretical maximum? Because Grok initially assumed a single shock inlet. And because I helped out Grok, I also helped out ChatGPT and asked it, are you sure that's right? And let's see the answers both of them gave us in the end. In this case, the trick to the trick question is that you can't slow down the air all the way, because by definition in a scramjet, the air reaches the combustor at more than Mach 1. In practice, significantly more than Mach 1, because really high compression ratios get impractical due to inlet design, because there's energy losses, and because, of course, in the combustor, the air in the combustor, the air heats up, so the speed of sound increases, so the Mach number decreases, it stays above Mach 1, so it has to come in at more than Mach 1. But we're asking for a simple theoretical maximum, so it should give us the pressure ratio it reaches as you take the air down from Mach 4 to Mach 1, and that would be around 80. In this case, both of them use the same equation, and both of them calculate for slowing down the air all the way to stagnation rather than down to Mach 1. So both of them are wrong. However, ChatGPT, in addition, they use the same assumptions, the same equation, the same, all the way to the last step they're doing the same thing, which is slightly wrong, but ChatGPT also messes up the math in the last calculation. 4.2 to the power of 3.5 is around 151, not 128. So Grok got that last step of the calculation right, which is better than ChatGPT, but it's still working under the wrong assumption. Also, Grok points out that you need flow greater than Mach 1, so this is not technically correct. It points that out, but it doesn't give us the correct answer. And then it talks about the practical design of an inlet. It is nice. I haven't checked all of this, but it means it does give us more information. It's slightly more useful than ChatGPT, because it tells us that it's wrong, and because it adds additional information, and because it doesn't mess up the last step of the calculation. They still work with the same wrong assumption, though. So they both got it wrong, but ChatGPT got it horribly wrong. Grok at least pointed the issue out. So I guess it's a little bit more helpful. Now, next question. Grok didn't want to answer anymore, so I had to switch browser. I made it a bit simpler anymore. Still made it a trick question, and apparently, if the question is simpler, they're more likely to fall for tricks. This one comes back to drag and aerodynamics. Two identical, typical airliners are flying, one at 200 knots, the other at 150 knots. Which one experiences more drag? And both of them answer that the slower airliner experiences less drag, the faster airliner experiences more drag, reasoning with a constant CD. ChatGPT even calculates as a ratio, because this is assuming the same shape, and thus at a lower speed less lift, so one of them would be falling down. What they're ignoring is induced drag, and 200 knots is slightly below the ideal speed for most typical airliners, so at 150 knots, due to induced drag, they're gonna experience more overall drag. because as you move faster, you get more drag from skin friction and your nose pushing through the air, but the faster you go, the less drag you get from the inefficiencies in your wings generating lift. Your wing has to push down air to generate lift. The faster you're going and the more air you push down, the more efficiently this can theoretically happen. The slower you get, the less air your wings get, the harder they have to push it down, and the more energy is lost to this turbulence, the steeper the angle the wing has to hit the air at, and the more induced drag you get. So as you get faster, your parasite and form drag increases, but your induced drag goes down. There's an ideal speed where they're equal, and with some simplified assumptions, it's basically one of them is proportional to v squared, the other one is proportional to 1 divided by v squared. Where they're equal, that's the ideal speed with the lowest overall drag, if you maintain lift. And for most typical airliners, that's a bit over 200 knots, indicated airspeed, so taking air density into account. And that means at 150 knots, you'd be experiencing more overall drag, which neither AI took into account. Funnily, you can translate the same phenomenon for helicopters, and if you do that, both of them get it right, although they don't get the correct explanation. ChatGPT assumes that the body generates aerodynamic lift, and that reduces the power required. Really, the power required is less because the rotor can affect more air and has a lower flow rate through it because it leaves its own tip turbulence behind itself. So you can create the same lift at a lower speed relative to the air moving through your rotor, a lower vertical speed, and thus need less power. So the explanation is wrong, and Grok doesn't really give an in-depth explanation, but they both get the correct answer at least. I asked ChatGPT another very basic one about rocketry. In space, what fuel theoretically has the highest chemical energy density? And, well, it kind of mixes things up and doesn't get the trick question I was trying to ask. It mixes up the total energy density and the fuel's energy density, because you can look up the energy density of hydrogen, of kerosene, of metals when you burn them, but this doesn't usually include the weight of the oxygen you have to carry to burn it. It does point that out as a correction for hydrogen. It doesn't do this calculation for the others. For hydrazine, it does take the oxidizer into account, but it just looks up a number and doesn't explain it further. For RP1, it just takes the energy density of the fuel. For metals, it just takes the energy density of the fuel. And it says hydrogen and oxygen has the highest energy density. That's not accurate. Metallic fuels have a higher energy density than hydrogen if you take the oxygen into account. The reason they're not very practical in space is because their combustion products have a high melting point, so you quickly get essentially ceramic snow forming if you try to expand that exhaust, and then you can't expand it further. It's not really useful as a rocket fuel as such, unless you go with a tripropellant and fluorine, but theoretically the chemical energy density of a lithium oxygen or aluminum oxygen mixture is higher than a hydrogen oxygen mixture. Doesn't really get that. Now a final simple trick question about spaceflight, and I was curious about Grok here because this kind of comes back to the whole Starship problem. How much lift would a spaceplane need to maintain altitude when re-entering at escape velocity? In this case, the trick is, if you're traveling at escape velocity, you try to maintain altitude, you've got a centripetal acceleration around the Earth of 2 g's downwards. Gravity pulls you down at 1 g, so that helps you. So you need 1 more g of downwards lift to maintain altitude. Grok is kind of on the right track here. It calculates the centripetal acceleration. it does the same step back and forth here, rather than getting the fundamental relationship there, and it uses gravity at some altitude. That's alright. Then it adds gravity to centripetal acceleration. It also assumes an arbitrary weight rather than just giving us the lift in g's that we need. Wasn't really part of the question, but it did ask for an amount of lift, so I guess I accept that misinterpretation. That's alright. The big problem here is gravity is helping you. So you should subtract gravity from this force to get the amount of lift you need rather than add it. So it gets 3 times the amount of lift you'd actually need, then does a very rough calculation for arbitrary dimensional assumptions and altitude, and comes to the conclusion that it doesn't work out. It wasn't really part of the question, and I mean, you could just go lower, then you heat up more. That's kind of the big problem. ChatGPT doesn't really do any of that. It points out that it would be difficult, and it does throw out 1G, but without the reasoning behind it. That is technically the correct answer. I doubt it's got the right reasoning. It kind of just explains that it's difficult. Not really correctly, but it happens to stumble on the right number in the end. And I asked one more slightly open-ended question about supersonic flow to ChatGPT. This one's again a relatively basic one, and it points out that things are complicated but doesn't actually give a concise answer that you might expect. Why are shock cones around jet fighters usually curved when the Mach cone should be a cone with a constant angle? And the obvious answer to anyone who's read about basic thermodynamics before is that as you compress air, it heats up. As you expand it, it cools down. If it's hotter, its speed of sound is greater. If it's colder, its speed of sound is lower. Same airspeed, different speed of sound, different Mach number, different shock cone angle. As the shock wave spreads out, the compression or expansion gets less intense and it approaches the ideal shock cone angle again. That's why they're rounded. That's why the low pressure zones start off with a pointier cone that curves to approach the ideal Mach cone angle, while the high pressure waves start off with a lateral sideways wave that curves backwards to approach the ideal Mach cone angle. It just points out that airflow is complicated. Shockwaves can interact, yeah, but if they propagated at the ideal angle, all of them at the same angle, they wouldn't collide to do that. And air density influences how they propagate, which is indirectly true, because if you compress it, it heats up, but it doesn't mention that temperature affects this. And it kind of just assumes that there are random variations in air conditions. It doesn't point out that a high pressure wave has a higher temperature and a low pressure wave has a lower temperature and thus a higher Mach number. And it comes up with the funny idea that maybe the jet's airspeed is just changing really fast. In conclusion, both AIs can look up formulas and fill them out, and they can do that at the level of a university student, but when it comes to thinking about aerospace engineering beyond Googling and using a calculator, they're kind of more on the level somewhere between an elementary school and middle school student. So, could either of them actually do my job? Well, no, and I kind of expected this. Like, fundamentally, they're not set up to think through all the details in a project. They can't really take that initiative. How helpful could they be? How much could they help? Well, reliably, not at all, because they get things wrong. When it comes to actual thought, even with very basic questions like early middle school level trick questions, they get actual thoughts wrong. They're surprisingly good at Googling and filling in equations. So they're a very well-spoken calculator that sometimes gets numbers wrong and misleads you into thinking that it can think. None of those qualities are useful in a calculator, so they're bad calculators. And also, well, what's actually inside here? I want to know. What's going on in here? What the heck is this? Why is it only on one side? What? Is there more hidden in here? Are there like Easter eggs? Wait. There's gotta be a reason this box is in here. Was that supposed to be the back of the head and it slid in here for some reason? Are any of these parts solidly connected, or do they just glitch through each other? And just how many models are stuck in here Z-fighting? I'm not sure I even want to know.